So next we have Dr. Michael Wagman, who will return to the topic of neutrinos and nuclei.
All right, thank you very much, Peter. So I'll get right into it. It is a triumph of modern physics that almost everything that we can measure in a lab is consistent with a standard model of particle physics that describes the basic building blocks of matter and only 4 possible low-energy interactions among them. The most familiar of these is gravity. It's what keeps us stuck here on the Earth, but gravity has very little effect on events that happen quickly over subatomic distances, and I'll be neglecting it for the rest of this talk, and you'll have to stay tuned for more from Lampros. The second is electromagnetism. It's what binds electrons to nuclei to form atoms, and electromagnetism also causes the protons in nuclei to repel each other. However, this repulsion is overwhelmed by a much stronger attraction from the uncreatively named strong nuclear force. And in the standard model, the strong nuclear force is understood as the exchange of gluons among quarks, the constituents of protons and neutrons. Finally, there's a weak nuclear force responsible for some of the radioactive decays that you were hearing about from Julieta earlier today, in particular the beta decay that I have pictured here, in which you could imagine starting with the unstable helium-7 and having a proton turn into a neutron to form lithium-7, emitting an electron and an invisible particle called a neutrino, or in this case, an antineutrino. And the standard model has had many experimental successes, but when someone tells you that they have a model that describes almost everything, you should ask about the almost. And if we can find experimental evidence for physics beyond the standard model, well, this gives us the opportunity to learn something fundamentally new about how the world works beyond the 4 forces pictured here. And to find those experiments today, we'll look at the neutrino. And as Julieta described, you need a source for a neutrino, like a nuclear reactor or a nuclear bomb. So we'll start a little simple and look at the sun for our neutrinos. Now, it wasn't always realized that the sun was a nuclear reactor emitting neutrinos. And in fact, the ancient Greeks instead theorized that the sun was a ball of fire carried on the back of a chariot by the god Helios through the sky every day. Now, from a modern point of view, chariot theory has a couple problems. Firstly, it doesn't really answer the big questions of what powers the sun and how it's lasted as long as it had, putting out all of this light. And secondly, the chariot is not observed. When astronomers started looking very closely at the sun in the 1800s, instead, what they found was evidence for a new element that they named helium in honor of Helios. And nuclear physics predicts that this element helium can be predicted by a chain of nuclear fusion reactions, starting with just a gas of protons that's collapsed under gravity, and that this could provide enough power to fuel the sun for billions of years. So the first step in this chain of reactions is proton-proton fusion, in which 2 protons fuse in order to form a deuteron, a nucleus with 1 proton and 1 neutron, emitting a neutrino and an anti-electron or positron. And these deuterons go on to fuse with other protons and eventually form helium-3 and helium-4. And since all of these nuclei are a little bit lighter than a collection of individual protons, these reactions release energy that's carried off by light and neutrinos to warm the Earth and the other planets. So last year, my collaborators and I made predictions for the proton-proton fusion rate starting directly from the standard model interactions of quarks and gluons. What we actually calculated was a lattice quantum field theory simulation in which we put 2 protons in a box, we applied a background neutrino field to the box, and we waited for one of the protons to turn into a neutron. And the strength of the response to this background neutrino field is related to the reaction rate for proton-proton fusion, as well as reaction rates for similar reactions. And our preliminary calculations so far are consistent with earlier nuclear models based off of fitting data to these other nuclear experiments. And with further refined calculations, we should actually be able to make predictions more precise than upcoming experiments like MUSUN trying to measure these reactions. So when people wanted to test the original nuclear models of these solar fusion reactions, they had to work a little harder. And the original experiments testing these realized that one prediction that you could test was the rate of neutrinos emitted by the sun. This is predicted by nuclear theory, and it's also something that you can go out and measure in a lab if you can detect the neutrinos coming from the sun. And in heroic experiments at the Homestake mine in the 1960s, Ray Davies and his collaborators took a tank of 100,000 gallons of cleaning fluid and were able to measure tens of atoms a day of chlorine out of that tank that were converted into argon by capturing a neutrino from the sun. And the rate they extracted from this experiment was, well, less than half the rate predicted by nuclear theory. And this led to a puzzle for a long time that was eventually resolved when it was realized that there are 3 types of neutrinos, and neutrinos that are emitted as one flavor can actually change flavors and oscillate mid-flight into the other flavors. And so nuclear theory predicts the right number of electron neutrinos emitted from the sun, but by the time they actually reach the Earth, they're in a roughly equal mixture of the 3 flavors, and the experiments at Homestake only detected the electron neutrinos that were left out of that. So we've since had experiments that are able to detect these neutrino oscillations more vividly and actually see oscillations from man-made neutrinos over scales of kilometers. And there are other particles that oscillate, so this isn't radically crazy. However, on theoretical grounds, neutrinos can only oscillate if they have mass. And here's where new physics enters the story. In the standard model, neutrinos don't have mass. Now, it's possible to add neutrino masses to the standard model by introducing some sort of new particles or forces. But there's not a unique way that you could add this mass, and all of the ways you could do it involve postulating that there's some new particles or forces that we haven't seen yet. So we'd like to understand what those are. What is the new physics beyond the standard model that's responsible for giving neutrinos mass? And a good way to start delving into that is by categorizing the different types of theories and seeing if there are different classes of theories that make different predictions for experiments that we can then go out and measure. And it turns out that the symmetries of the standard model provide a good way to start classifying these theories of neutrino mass. And the standard model has some symmetries and conservation laws in it. And one of them is that lepton number is always conserved. So if you take any reaction in the standard model and count the number of electrons plus the number of neutrinos minus the number of anti-electrons and neutrinos produced, this number will always be 0. So this reaction that I have here on the left conserves lepton number. So this is a cartoon of the very unstable hydrogen-7 decaying into lithium-7, where 2 protons simultaneously turn into neutrons, emitting an electron and an antineutrino. So you might recognize this as just 2 copies of the beta decay reaction that I showed earlier. And so this is a double beta decay reaction that conserves lepton number and is allowed in the standard model. On the right, I have a similar reaction in which the 2 would-be antineutrinos join and annihilate like a neutrino and an antineutrino, leaving just the 2 electrons emitted and nothing else. So this neutrinoless double beta decay reaction violates lepton number and is manifestly not allowed in the standard model. So if this lepton number non-conserving interaction giving rise to neutrino mass existed, it would have interesting consequences. And if you have lepton number not conserved, this means that there's no conservation of particle numbers left in this extension of the standard model. And in high energy reactions, it's possible to turn matter into antimatter. And this might give us clues for how a post-Big Bang universe, hypothesized to be a roughly equal mixture of matter and antimatter, could dynamically evolve into the matter-dominated universe that we see today. Now, this possibility might seem a little out there, but it's actually theoretically very well motivated. And if you imagine that there are no new low-energy particles that we're going to find, then you can organize all of the possible new interactions of standard model particles in a low-energy expansion. And the leading term in this low-energy expansion, besides the standard model forces that we know and love, is actually an interaction that gives rise to this lepton number non-conserving type of neutrino mass. So if we can measure the strength of this lepton number non-conserving neutrino mass, this could tell us both the answers to questions about how matter came to dominate over antimatter and also offer us strong hints as to where we might expect to find new physics beyond the standard model and at what scales we might expect new particles and interactions to exist. So experimentalists around the world have taken up this challenge and are looking for neutrinoless double beta decay in a handful of special nuclei where double beta decay is allowed and single beta decay is not. So for instance, the Quarry experiment that Lindley Winslow's group here at MIT and other groups around the world are involved in is searching for the neutrinoless double beta decay of a tellurium nucleus with 130 total protons and neutrons turning into a xenon nucleus with 130 protons and neutrons. So Julieta talked to you about the prospects and challenges for experimental detection of neutrinoless double beta decay. In a very, very short theory summary, the current experiments either will or will not detect neutrinoless double beta decay. Now, if the experiments do detect double beta decay, then theorists have work to do. The goal of these experiments is to understand the new interactions giving rise to neutrino mass, and the only way that we can do that is if we actually start from these theories and make predictions for what the experimentalists measured, these neutrinoless double beta decay reaction rates. And ideally, we'd like to make predictions that include some model of the neutrino mass, and also include all of the standard model interactions and the strong nuclear forces that are happening during this nuclear reaction. So what we'd like to do is do simulations starting with the standard model interactions of quarks and gluons, where we add in these sort of neutrinoless double beta decay producing neutrino masses. Okay. Now, on the other hand, if the experiments in the current generation don't detect neutrinoless double beta decay, well, then theory has work to do. Because the goal of the experiments is to still understand the nature of neutrino mass and the new physics giving rise to it. And the experiments in this case would be hinting that it's not this lepton number non-conserving possibility. So if you want to actually test that and falsify these theories of lepton number non-conserving neutrino mass in the no detection scenario, you again need reliable theory calculations starting with these theories of neutrino mass, predicting the neutrinoless double beta decay reaction rates that can be compared to data if you want to test the theories. So currently, we're able to do simulations starting directly from the standard model for small nuclei. And my collaborators and I have now performed simulations of 2 neutrons in a box, where, you might have guessed it, we apply a background neutrino field and wait for a double beta decay reaction, turning these 2 neutrons into 2 protons. And we relate the response of this background neutrino field to the rate for double beta decay with neutrinos, in this case, in a 2-neutron system. Now, this isn't itself experimentally relevant, but we then went and calculated the same reaction in a simpler model of nuclei. And we're able to tune the parameters of this model to reproduce our precise calculations from the standard model. And so in this way, we can imagine that these simulations of small nuclei that make very few approximations and make precise predictions starting from the standard model can actually be used to inform these simpler models and effective field theories that can then go make predictions for the nuclei that experimentalists actually measure. And this is important because these effective field theories and nuclear models are the best that we have today, and they're what's being used to make decisions about designing these experiments and to understand what is the probability of finding this sort of reaction in different nuclei and which nuclei should we be going out there and looking for this in. Ultimately, though, what I'm interested in doing is making calculations of these neutrinoless double beta decay rates starting directly from standard model interactions with no uncontrolled approximations or nuclear theory uncertainties. And if you want to use low-energy nuclear physics as a precision tool for constraining beyond the standard model physics, then this is the direction that you need to go. However, I've said that we can't actually just do this picture and put tellurium-130 in our lattice quantum field theory simulation and apply a background neutrino field, so why not? And the reason why not goes by the name of the signal-to-noise problem. So I have a plot here of some of our data from one of these simulations. And this is data for the masses of these hydrogen and helium nuclei that you met in the solar fusion chain. And all you need to know is that our results are found by extrapolating to the right in this plot, which you can think of as something like a time variable, and then the increasingly large nuclei are the lines going up in this plot. So what happens is that there's an exponentially bad signal-to-noise problem, where these error bars representing the noise in our simulations get larger exponentially as we increase the number of protons and neutrons in the simulation. So if you tried to take this method and just extend up to the line for tellurium-130, all the computers in the world won't get you a simulation where you have enough data points to actually make a reliable fit here. So we need to think about some more clever ways to approach this. And in my PhD work, I worked on relating this signal-to-noise problem to a generic obstacle for numerical simulations called the sine problem. And it's easiest to explain by example. So imagine that you're trapped on a desert island and want to try and calculate pi. One way to do this is by drawing a square in the sand, uniformly dropping rocks throughout the square, and then standing in the middle and measuring how many land within a unit radius of you. And from this, you can get the fraction of rocks in the circle and the ratio of the area of the circle to the area of the square, and from that, pi. And this eventually converges to the right answer, and on this plot of the error, you can see a steady decrease in your error on your estimate of pi as you increase the number of samples. And this is a log-log plot, so this line is pretty good. Now, let me change the problem slightly, and imagine that you can drop rocks anywhere in the right half of the square. but only on some fraction of the left half. And I ask you to estimate what that fraction is. Well, one way you can do it is calculate the area of the right half, the area of the left half, and then take the difference of them. But in taking this difference, you need to introduce a minus sign that gives the sign problem its name. And the problem is that trying to estimate a very small number from differences of larger numbers is an imprecise thing. And until you get a very large number of tens of thousands of samples, you can't really average your large numbers down to small numbers and start decreasing the error on your estimate of this 0.05 in this case. And you can see this slow, steady error until it finally starts decreasing at a very large sample number. So this is what we'd like to avoid. Now, linking this to the nuclear physics signal-to-noise problem starts by recognizing that what we're really simulating are complex numbers. And complex numbers have a magnitude, which is positive, but they also have a phase, which you can think of as parametrizing some angle on a circle. And the fluctuations of this complex phase are sort of like a random walk of a bead on a hoop. And if your bead doesn't travel very far, then it's just as easy to estimate how far it traveled on the hoop as it would be on a line. However, if your bead fluctuates all the way around the hoop, and all you have is snapshots of where it started and finished, then you might wildly misjudge how far it actually traveled, which would not be a problem if you could unwrap this circle and just watch your bead fluctuating on a line. So this problem of trying to estimate the width of something taking a random walk on a circle actually has a sign problem. And if you just have normal random variables, then you can estimate the width of the distribution by averaging positive numbers, no sign problem, and these blue lines, the error is decreasing nicely. However, if you imagine that your random variables live on a circle, and you just have some 2 pi interval here that you wrap all of your data points around onto, then trying to estimate the width of a large distribution on a circle actually requires taking differences, has a sign problem, and has this same pathological behavior where the error doesn't really start decreasing until you get tens of thousands of samples and can start estimating small numbers from differences of big numbers. So this problem then presents us with a toy model for the signal-to-noise problem that we see in nuclear physics. And working with Will Detmold and a graduate student, Gurtej Kamwar, here at MIT this year, we've actually turned this toy model into a full-blown lattice quantum field theory simulation of random phases. And you can see this plot up here on the upper left looks sort of like the plot I showed you before, with exponentially growing noise as we go further in simulation time and up in the number of particles that we're putting on our hoop. Now, if you take this idea, what we want to do is unwrap these fluctuations of random angles onto fluctuations on a line. And if you assume that your fluctuations are smooth, then there's a mathematically well-defined way to do this and to relate what you get out to the physics that you want. And by assuming that you jump less than halfway around the circle, for instance, you can get a rule for how to define these unwrapped phases. And when we look at the spectrum of particles on a circle after doing this phase unwrapping, we see that we get rid of this exponential growth in our noise as we increase the number of particles. The caveat is that when we look at our practical simulations, the phase jumps aren't as smooth as we want them to be. And there are some cases here where our wrapped phase, the green lines here, slowly cross below this sort of line, jump up to the other side of the circle, and it's easy to recognize this as what's happening. But there are other cases where there are jumps of around half the circle, and in this case, different methods for defining this unwrapped phase will give you different answers. You have an ambiguity in how exactly you want to do this calculation, and this can lead to potentially large errors that we don't have a good way to control. So in trying to understand how to do better with this, what we've come to realize is that similar phase unwrapping techniques have actually been applied for decades in diverse fields of signal processing, science, and engineering, including nuclear magnetic resonance imaging, radar tomography, and X-ray crystallography. And what people have found in these applications is that the multidimensional phase unwrapping problem is actually much better posed than the one-dimensional problem. The basic reason is that in one dimension, there's only one line you can choose between point A and point B, But in higher dimensions, you could choose different lines. Imagine doing your unwrapping along these different lines and then check for consistency between your results. And this allows you to start building in error correction and redundancy into your algorithms. So we're hard at work now trying to understand if we can use these sort of multidimensional phase unwrapping algorithms to get a more robust handle on the signal-to-noise problem that would eventually allow us to do simulations of larger nuclei. So just to recap, neutrino experiments let us see beyond the standard model. And detection of neutrinoless double beta decay would allow us to understand the nature of neutrino mass and physics beyond the standard model if we can make reliable predictions from these theories for the large nuclei involved in these experiments. And so we're hopeful that in my next couple years at MIT, we can try and unwrap the sign problem and do direct simulations of large nuclei. So I'd like to give a big thanks to Neil and Jane for supporting my research program here, and also shout outs to my collaborators in the nuclear physics from Lattice QCD collaboration who were involved in the simulations of proton-proton fusion and double beta decay that I discussed, as well as the Lattice quantum field theory group here at MIT, and everyone up at the MIT Bates lab who keeps the hardware running and fends off the squirrels constantly trying to attack it. So thank you very much.
In pursuing an alternative algorithm that presumably will minimize the wide fluctuations you're getting, is the speed of that computer limiting you in the sense that if we had a computer 10 times faster?
Yes and no. It's limiting us in the sense of if we had a computer a billion times faster, then we could just do it. Then there would be no problem, we could just run. But the scale of the computational problem of doing a nucleus with 100 protons and neutrons is off the charts for the available computing capability of humanity today.
Is it a speed issue or a memory issue? Or a little bit of both?
Memory is always a problem, but this is mostly a speed issue in that you need to, what we really do is we do many different random simulations and then we average over them. And right now we'll do sort of order 100,000 or 1 million simulations of these protons in a box to average things over. If we wanted to do these nuclei, we need to do e to the 100 squared times more simulations, which just gets to be a really unfeasibly large number of compute hours in this case.
So are then you pursuing alternative algorithms, which like
right. So what
that's
I'm
the
really
primary focus?
I mean, if we want to be able to do direct simulations of large nuclei, that's what we need to do. So I'm also interested in these methods of trying to connect to effective field theories and simpler models of nuclei, and sort of that approach towards getting to large nuclei. But if we want to do a direct approach where we just start from quarks and gluons, then we need an algorithm that scales polynomially instead of exponentially in particle number.
And the reason you want large atoms is because that's what they're using in the experiments?
Correct.
So is there perhaps going to be some convergence? Might some of these experiments start to be done with smaller atoms? And you go up and they go down and you meet in the middle?
How much I love calcium-48. But the problem is that there are only these certain special nuclei that double beta decay without single beta decaying, and there aren't any lighter than 40-some protons and neutrons, which is off the charts from what we can do today.
40 is still better than...
40 is a lot better than 130, but it's still way more than 4.
Other questions from the audience? Okay, let's thank Michael again.